The concept of quality diversity optimization is a quite recent concept that has been introduced a couple of years ago. And the objective of quality diversity optimization is to optimize in a single optimization process a large collection of solutions that are both diverse and high performing. So we usually use this schema here in order to represent the objective. So we have our search space, so exactly like in evolutionary strategies, where we have a real value search space, and the goal is to find which point in this hyperspace or high dimensional space will lead to the most interesting solution. And so we want to explore this space via the quality diversity algorithm in order to generate a list of diverse solutions according to the behavioral descriptor space. So using the concept of behavioral descriptors that we have seen in the previous video. And for every region of the behavioral descriptor space, we want to have the best solution as possible. So we want to have a high diversity by covering well this space. And we want also to have a high performance because we want to have the highest solution for every region of this space. So we want to only keep the green dots at the top of this space. So that's why we have a quality diversity, because we improve the quality and the diversity at the same time. So I will give you an example of application to give you a concrete idea of how that can be used. So imagine you have this hexapod robot that has 12 degrees of freedom, so 12 motors, 2 per leg, one here and one here, one to control other leg can move back and forth, and another that will control the elevation of the robot, of the leg. And every joint here can be controlled with this kind of sine wave that is parameterized according to the amplitude, the phase, and the duty cycle of the figure. And every solution, every joint is actually controlled by this kind of sine wave. So we have 12 degrees of freedom and times 3 parameters, so 36 dimensions. And so that's the genotype. So that are 36 real valued parameters search space. And here we have the behavioral descriptor, which is the proportion of time that each leg is in contact with the ground, that we can discretize into different values. So that's a 6-dimensional behavioral descriptor space. So the goal here is to try to find the parameters of this genotype here that will lead to different ways to walk. The goal is to walk as fast as possible. So here, by using this fitness function, that is considering the position of the robot after 5 seconds, so on the x-axis, so how much distance the robot managed to travel in 5 seconds. And we will use the description, the behavioral descriptor, in order to find different way to solve this task by touching the ground more or less with different legs. So we run this algorithm, so the MapEdit algorithm, that I will introduce in the next video during 40 millions of evaluation. I will give all the details later. And so you will even be able to almost reproduce this if you have access to a physical simulator. And the result is that the algorithm managed to find more than 13,000 different ways to walk. So here in this complex figure, the most important things to understand, it's that every colored pixel in this matrix represents a different way to walk. It's just a way to represent this collection of solutions that we have obtained in a 2D space from the 6-dimensional space into 2D. So every colored pixel is a different way to walk, and the color of the pixel corresponds to the speed of the robot. So the more red is the pixel, the faster goes the robot. And so you can see we have a lot of different solutions, and to give you some ideas, we have some gates or some walking gate here that are using more or less all the legs uniformly and with uniform contact with the ground. We have in this large collection of solutions some gates that are using some leg a little bit less than others. So typically the legs that are circled in red at the beginning, like now, are in contact with the ground less than 10% of the time. And what is interesting is that when I ran this algorithm during my PhD, I realized that the algorithm managed to find this solution that is quite surprising. The algorithm managed to find a solution that was making the robot walk without touching the ground with all the legs more than 10% of the time. So that was quite surprising, and at first I thought it was a bug in the code, but no, this is the solution that the algorithm managed to find. He found a way to let the robot flip on his back and walk on his knee and continue to walk. And because we are actually just computing the contact with the ground only at the tip of the leg, then the algorithm found a way to fool the matrix and find some new solution. So that's a very good illustration of the creativity behind this kind of divergent search aspect that we can find in novelty search, but also in quality diversity algorithm. And just to go a little bit further, why it is useful to have this kind of diversity of solution, and so that's some results that we have obtained in a Nature paper that I published a couple of years ago, where we apply the obtained solution that I showed you just before on this physical robot. It's a relatively simple robot that we have in the lab. I would usually make a demonstration during the lecture, but here you will have only access to the video for this year. And so what this robot is composed, again, a couple of motors and embedded computers in the center, and just a single sensor here, which is this 3D cameras that it will just tell the robot how fast the robot is walking on a straight line. So you can see no fancy sensors, nothing very, very complex here. And so when the robot is intact, initially we can use an open loop controller, something that we call a tripod gate. And we can see that when everything is going well, the robot walks at a speed of 25 centimeters per second. But we can imagine that a damage occurs. So typically here, what I have done is I've simply disconnected one cable here, which is quite actually a realistic scenario that can happen on complex robots like the robot we sent into a mission on Mars, because placing a cover to protect the cable is actually creating additional weights that can actually be challenging in space mission when the weight of the robot is difficult. And so the goal is to use the collection of solutions that we have in order to see if we can adapt to this situation. So you can see typically that this small damage has a big impact on the robot, because now the performance of the robot, which is, I recall, going straight forward as fast as possible, significantly decreased. And so we generated, or we introduced a new algorithm that is called the intelligent trial and error algorithm. So that's not really the topic of this lecture, but that is just an algorithm that uses the collection of solutions obtained by the quality diversity algorithm here, the one that I showed you before. And we use Bayesian optimization and some variant of Bayesian optimization that you might see in some other course at Imperial, in order to quickly search this collection in order to find the solution that works the best. And so here you can see the robot has selected different solutions, observed the performance, and selected the new solution so far. And before the shot, just before this one, you saw that the robot managed to learn something quite interesting, but the robot continued to explore because maybe something better did exist. But after this trial, the robot was able to unsupervisedly decide that it was sufficient and stopped. And so here you managed to see that in less than 40 seconds, the robot managed to learn a new walking gait, so this one, which was very close to the initial performance, even in the presence of a broken leg. And slow motion actually reveals that this gait is actually quite dynamical, so using the back legs to push the robot forward, and in order to avoid using the middle legs and solve the task in a different way. This kind of dynamical motion is actually quite difficult to train with gradient descent, because actually the fitness or the fitness landscape or the gradient is actually very discontinuous with a lot of peaks and valleys, and it's very hard to not get stuck in local optimum. But here, thanks to the quality diversity algorithm, we can use it. Another example, a broken leg here. You can see the same effect. The performance is quite deteriorated by this problem, but after only 25 seconds, the algorithm managed to find a new solution. So we tried a lot of different examples. So for instance, when we have the broken leg and the disconnected leg, but also when the robot is intact, in order to solve a problem that is called the reality gap problem. So it's the difference between simulation and reality. Some example where we remove completely one leg or two legs. Also an example where we roughly repair the legs with just a piece of wood and a couple of screws. So the size of the leg is more or less the same as the intact leg, but the shape and the material is different, which induce a difference in the performance. So here, with the yellow star, you can see the performance of the initial controller before adaptation. So when the robot is damaged, you can see that the performance is very bad. When it's intact, it's quite good, so 25 centimeters per second. And the blue distribution here is the performance of our algorithm after trying it 40 times per condition. And here you can see the amount of time every condition required to adapt. So you can see that in average, with this approach, we managed to learn how to adapt to all the situation in less than 2 minutes, except when we remove 2 legs, which is quite severe. In here, it requires a bit less than 3 minutes. So that was kind of an example to show you how powerful the concept of quality diversity is and why generating this collection of diverse and high-performing solutions can be very useful. Of course, all the details and challenges of the intelligent trial and error algorithm will not be at the exam. It's just, again, an illustrative example. So now let's dive into how quality diversity works. So there are multiple quality diversity algorithms that exist, multiple variants, but most of them can be summarized in this schema, where we have this collection of solutions that we try to build. So initially, the collection can be generated by just creating some random solution and adding them to the collection. And then we use a stochastic selection operator to randomly select a solution depending on some bias or some heuristic. And then we apply a mutation. We can also apply a crossover. We can then evaluate the new solution and try to add them in the collection. So that's a generic pseudocode, but I will show you a more concrete example a little bit later in the next video about MapElite. And the two main things that are important in quality diversity is that in order to build this collection of high-performing and diverse solutions, we need to be able to measure the performance of the solution, and we need to distinguish between the different types of solutions that are observed. And for this, we will use two concepts that we already have covered in previous lectures. So first, the fitness function. So literally the same definition as all the algorithms that we have seen so far, and the behavioral descriptor that we have seen in the previous video about novelty search. Sometimes in the literature you can also find the word behavioral characterization, that's just another name for the same definition. So in order to give you an example of a quality diversity algorithm, the name of this algorithm is novelty search, but with local competition. So it's an extension of the novelty search algorithm. So if you recall the previous video, we had this novelty search algorithm where we rank the solution according to the novelty score, and we use the novelty archive. And novelty search with local competition will actually use a multi-objective evolutionary algorithm. So because of this, it's a going further concept. It will not be at the exam because we did not cover in this course multi-objective algorithm. But you can easily understand the concept here because it's optimizing actually two fitness function at the same time, the novelty score in one hand and the local competition in the other hand. And the idea is in this case, to try to find diverse creatures, but also creatures that are working as fast as possible. But we don't want to compare our new creature to solutions that are definitely not working in the same category. So you will never, for instance, compare the speed or the velocity of a tortoise with the velocity of a ball. That doesn't make sense. So that's why we have this notion of local competition, because you might want to actually consider or compare or make the two different solutions compete only against similar type of solution. So typically here we will have the tortoise competing against only the k nearest neighbor, the same neighbors that we use in novelty search. And the way the local competition score is used is simply the number of the k nearest neighbor here that the solution outperforms. So here you can see that the tortoise outperform the snail, but doesn't outperform the donkey and the goat. So here the local competition score will be only 1. And so if we find another type of tortoise that is going faster, for instance, or than the goat, then we will use it, and that will lead to a quality diversity algorithm. So just a note, when the novelty search with local competition algorithm got introduced in 2011, the concept of quality diversity was not already introduced, and it's only a couple of years later that we propose that to see this algorithm as a QD algorithm when we combine it with an archive management system. So typically, every time that we find a solution that is actually better than this one, so if we find, like I say, a new variant of tortoise that works faster than the current one, we will discard the already existing tortoise in our collection, and we will replace it with our new better tortoise, and that will become eventually a quality diversity algorithm, because this novelty archive will start to include novel solution, and every time we have a novel solution we will add it, like what we did with the tortoise, but it will also include more and more better solution by this mechanism to replace solution when we found better ones. So typically the author of the novelty search with local competition has used this algorithm, for instance, to generate different virtual creatures of different shapes and different morphologies, and they try to find those different creatures by also finding those that work as fast as possible. And so here they had two different metrics in their behavior descriptor: the age of the creature and their mass. And so you can see that if you optimize only the novelty of the solution using the novelty search approach, you might be able to cover the entire space, but the performance of the solution, that is denoted by the color of the dots here, the darker is the dots, the more fast the creature can walk. You can see here that the solutions that are found are quite slow in general, so even if we cover everything, we don't have a good exploration of the performance of the solution. If we do a fitness only, we have the same behavior as before, so the population quickly converging to only one zone of solution, only having high performance. When we have the novelty search but with a global competition here, we can see that we fail to explore everything, and we have mainly one cluster of solutions that is gathered in the same region of good solution. And so that's why it's important to sometimes consider the local competitions, only comparing the fitness between solutions that are close, so between the k nearest neighbor, that will enable the solution to explore all the space of possible solution and create a lot of small clusters, only comparing the good solutions. So here you can see that eventually we have, as a result, a lot of good solutions spread across all the diversity of spectrum we can find, and across all the space we have high-performing solution. So this is the first introduction on the quality diversity algorithm, explaining first of all why it is important to generate solutions that are diverse and high performing, and giving a small example of one of those algorithms, novelty search with local competition. And in the next video we will see a little bit more in details one of the main algorithms that you need to know about quality diversity, which is a map-it algorithm, a simple but yet very effective quality diversity algorithm. So I will see you on the next video to talk more about quality diversity.